Alright, what we want to do right now is to take a look at a velocity versus time graph and analyze this graph so that we can come up with some equations of motion that we can use instead of always going back to a graph. Graphs are very helpful to figure out the relationships between variables, in this case velocity and time, but we don't want to be doing that over and over and over again. What we want to find is a general relationship based on this graph that we can then use to solve problems and analyze new scenarios that have similar properties. So what we would have done in lab is have a car accelerate from one velocity to another velocity over a certain amount of time. And the example that I often use in class is the fact that my wife's favorite car to drive when she was younger was a BMW SUV that when she nannied for a rich family. And it had a great acceleration when going on the highway, when going from 30 miles an hour, which is approximately 20 meters per second. Sorry, 15 meters per second, not 20, to say 70 miles an hour, which is about 30 meters per second, 32 meters per second, over the course of about 3 seconds. So a graph of that motion wouldn't be a general VO and a general VF and a general time. It would be, we're starting at about 15 meters per second, and we're going to end up at 32 meters per second, and let's say that it takes 4 seconds. It's very important to be able to do this and to have this calculated so that when you're merging onto the highway, you can get up to the highway speed and going at, a lot of cars start out going roughly 30 miles an hour on the entrance ramp, and then you need to accelerate up to the same speed as what everybody else is going so they don't crash into you, which is often about 70 miles an hour or 32 meters per second. These are rough numbers. And you need to do that in a short amount of time. If it takes too long, then cars are going to be whizzing by you, honking at you, and you're never going to get off the shoulder. So car manufacturers have to be able to calculate the acceleration of their vehicles. Well, the acceleration in this case is going to be the slope of that line. So for velocity versus time graph, slope equals acceleration. What's the acceleration for this particular car? Well, you need to remember the formula for slope. Formula for slope is often written as m equals delta y over delta x. If you're not familiar with delta notation, you take 2 points, x2, x1 and y1, and x2 and x1, and what we're going to do is subtract them. So this point right here would be x1, which is 0 for time, and y1, which is 15 for the speed. And then up here is the other point, x2, which is 4 seconds, and y2, which is 32 meters per second. And we can plug them into this formula from math class, where we have 32 minus 15 over 4, and we will have 17 over 4. And when we divide those guys, we get an acceleration of 4.25, and we need to have units. I've been saying that the units of the velocity are in meters per second, and the units of the time are in seconds. We can move the S over there to the time axis label. So when we divide these guys, we're dividing meters per second by second. So we could write this as meters per second, but nobody ever does. The way we write it is 4.25 meters per second squared. All right, that's all well and good for this particular problem. But what if we're making a new car not that BMW SUV that my wife was driving when she was a nanny. What if we make a new car and it's not going to have the same engine and the same body? It's also going to be able to accelerate from one speed to another speed. What would that look like when we use, again, our formula for slope, but then plug in these letters that we have in physics class? So the slope, still going to be slope m, and now we're going to have y2 is going to turn into VF. And we're going to subtract y1, and y1 is now VO. Instead of having specific numbers, we have the names of, or the symbols that we use. V for velocity, O is original, V for velocity again, and now it's the final velocity. And we're going to have the time t, however long that takes, minus 0. And that is going to be called the acceleration. So over here, instead of just saying slope, in physics class we will say acceleration, because we're changing the velocity by time. We can clean this up a little bit and say VF minus VO over T, and we will do that because we always want to start out with our stopwatches cleared for 0 seconds. We can rewrite this equation, A equals VF minus VO over T, and that is one way to have this equation. If we were in class with equation cards and everything, I would say take out your equation card and write this down. Typically, however, we rearrange this equation a little bit so we don't have a division in the equation. What we do is we multiply both sides by t. Multiply both sides by t. Disappears from the right because we were dividing by t, and then we multiply by t, they cancel out. Now we have a times t on the left. I'm going to have to come down here because I ran out of space. So now we have VF minus VO equals a times t. Again, I prefer to have the equation where the VF is all by itself. So at this point, what I do is I add VO to both sides, and it disappears on the right, and it reappears on the left. And what we get is VO plus A times T equals VF. And this is A times T. Or you could write it as, instead of with a little star there, you could write it inside parentheses, and we'll have A and T. And this is an equation that is worth memorizing because you'll end up using it a lot. Next, we want to talk about some other kinematic equations, because this is only one of them that includes 4 of the quantities that we will use in kinematics: an original speed, an acceleration, a time, and a final speed. The acceleration and time are multiplied, and then they are added to the original speed.